My intent here is a little different than most of these things. There's no point in trying to give you a cookbook answer to grounding and what you might want to do with your station. That is all over the internet, so many places. And one of the things that drives me crazy is some people say this is a controversial topic. It should not be. Um, uh, all of these questions, like people say, okay, well, there's an RF ground and there's an AC ground and there's a lightning ground and all this kind of stuff. And of course, we're grounding everything. So, what the heck does ground mean? That's the real question. So, uh, we're wondering about a lot of these things. Like for example, this term ground loop, which I absolutely hate, and we'll talk about that a little later. Um, but most important to realize that grounding is an engineering problem. It is a problem that needs to be solved with proper technology. I can see that. Some of you will be scratching your heads like Vince on the problems he had in his station. And problems will crop up, but the thing is to start proper with your station, and then the problems should be a lot fewer and farther between. Now, as per engineering, engineering is optimization, and it's optimization for safety and for performance and for cost. And of course, those things concern all of us. We've got to approach it as a system. You can't just do one piece of it and not look at everything else. And that is really that's my soapbox tonight. Let's look at everything. Let's look at what happens, with currents in a station, because really that's really what is happening here. So we've got to plan our station for growth and improvement. It would be really nice if you could start with building your house and putting the tower on the property and all that. But most of us has to do with make do with what we have. In part one, we'll look at basics and understand what's happening, and then we'll take our break. And then part two, we'll build up a station, and there we will look at a lot of specifics and grounding pictures and other resources. So Jerry suggested that I put my conclusion slide first, and I won't take much time on this one, but here's some major points. We have many currents, and they're sharing common conductors, and that is something we call ground. These conductors should present low Z, including low resistance. We often have a lot of signals flowing in ground, and that can be compatible. It doesn't mean to say that various currents are going to be incompatible, but we must have the system fully integrated, and we must plan it all for the conductors that are going to be common. So I know this sounds like a lot of stuff right now, but in the end, we will have a look at it as we finish part one. Now, this picture, and I say confusing and so forth, and you look at that saying, wow, we're right into it. There's a nice bus bar there, and here's our PC and our accessories and that. They're all tied to this brown bus and a ground rod and everything else. And this is exactly what ARL and so many other sites say. And this actually was and it was on a Flex Radio article. And I will show you the article if we have time. But the thing that drives me crazy is this guy's run ground loops on here. Like, what is a ground loop and why are there ground loops? And as far as I'm concerned, that's nonsense, or probably is nonsense. So watch out for what you read. So maybe the most important slide of all. This is really important. And you say, well, we know this stuff. Current, what's current? We know it's a flow of electrons, can be DC or AC. And of course, it can be an impulse like lightning. And the reason that that I entitled this presentation "Current Control" is because that's what we want to do. We want to decide where we want currents and where we don't want currents, and where we have currents, how do they affect other currents? How do they affect us? And so that's important. And we must remember that current can be conducted. It's flowing in a wire as while we do our business. or it can be induced. You know, there's some wires hanging underneath your antenna, and voila, you've got a lot of current flowing in that wire. Maybe you didn't want it. And also, once you get a current, it can generate its own field and can cause currents in other wires. Okay, so that's all basic stuff, but you say, well, so what? Now, very important, voltage is a potential difference. You have to remember that. It's just like height. You can't say height, something is so high without saying with respect to what. You know, when Ken goes up a mountain, they say it's up at 9,000 feet. Well, you have to have a reference, of course. And so voltage is only in existence because of one of two things. Either you have a current flow, V equals IR across a resistor, or you have a static charge. Like you have two objects that are at a different potential from one another, for example, like the cloud and the ground, okay? Skin effect. This is very important. Skin effect, we've all heard of. And you can see a little chart here that what we are 0.1 millimeters at 1 megahertz or something like that. Yeah, it's very, very shallow and does very much with the type of material. But this is of concern when we start to design our grounding systems. And of course, we've all heard this, that braid or strap is a good idea, right? As it turns out, it's not a real concern for AC, that means AC power line, or for lightning. Now, lightning's a different cat. It's a real concern, but skin effect really is not that much of a concern there. Although obviously, the better the skin depth, the better conduction we're going to have. Inductance. Now, this is a biggie, especially when we talk about something like lightning, because if you remember, my best definition of inductance is something that opposes a change in current. And microhenries do matter. Inductance, of course, can be used to control currents, unwanted RF currents. But when you have lightning hitting a wire, and you know, I've seen so many. Last night I spent time watching about 7 or 8 videos on people's stations and what they've done for lightning protection. And you know, I must reiterate, I am not an expert in this stuff. I am not an engineer. All of this stuff is really for our own edification, and I always recommend that you get your own advice, and especially professional advice. And any question about insurance or that kind of stuff, you know, don't take me for gospel there. But anyway, these videos that I saw, they have, you know, they have wires streaking around like this. They're not straight, and they're not well mounted. They're not secured, and it just looks like a rat's nest. So never mind what it looks like, but any kind of excessive wire, curved wire, coiled wire causes inductance, and that can be bad. It can be good, depending what you want to do. So reactance, of course, is inductive or capacitive, and that really is a combination of a resistance and inductive or capacitive reactance there, and um, and of course the two together make impedance. Now, here's our first idea of what we're trying to do here. We all know that you got a battery and a bulb and a switch, and you can make a complete circuit. My young niece at grade 5 just finished the batteries and bulbs unit, which is just kind of amusing. That's where it's taught in school. Now, have a look at the circuit below it. Is it a complete circuit? Well, we kind of think it is. What's the connection in the loop between those two funny little symbols? Of course, they're ground symbols. But this is a path for currents that is convenient. It's a return path. I had a look at a lot of schematics, and a lot of them are not using ground symbols anymore. They're using just straight lines, and I think that's a kind of a, well, it's a difference in thinking, and it's a difference in building too. If we go to an idea here of what grounding is, grounding is an often misunderstood term, and in fact, it's kind of word like signal. It's used so much that unless you specify what you're talking about, the word ground or grounding is almost meaningless. This is I can't stress that idea enough. So, but let's have a look at this circuit here. You say, "Whoa, what's all that stuff?" But it's just a simple little circuit. In fact, Gordon probably remembers it. We use this in a lab at work. It's part of a little PSK receiver, I guess. The point D on the left is an antenna, some protection diodes, and on the right, you finally end up at your headphones and, mixer and crystal filter in between and yada, yada. My point is, what are all these little funny ground symbols? What does that connect to? Well, it connects to a common ground plane. I'm going to call it that, some common conductor on the circuit board where this is made. And what's flowing in here? Well, of course, there's the RF, antenna coming in here with respect to ground on a chassis connector. There's going to be bias because they got B plus at the top. And you've got that's DC, of course. And who knows? Maybe you're going to have AC hum induced in here somewhere. So we don't know really what's being conducted in the ground. And if you think about that ground and you go back a slide or two, and I think it's worth going back here to that slide and saying, okay, if there is no resistance, and the skin effect is minimal, and no inductance in the ground plane, then it is pretty good. It's ideal, and it doesn't cause us any problem. People that do design, though, they know that sometimes you can get into trouble and you have currents flowing and they'll cause a voltage drop, and that will get into other circuits. Here's an example that some of you might be familiar with. I think Ken and some of the others were playing with this stuff, but a question that was asked, well, why do we have a common ground separate for digital and for analog circuits? And the reason is that digital circuits are notorious, especially the old TTL, notorious for these severe current spikes. And they used to recommend a bypass capacitor every 2 chips. And of course, CMOS is not so bad, but in any case, it has its own noise. And if that were common, and I left off the other slide showing what happens if you put the grounds together, and I think you can imagine that if you connected the grounds, the bottom ends of the analog and digital circuits together and had one common wire, then you would be injecting in series digital noise into the analog return. And so, of course, we don't want to do that. So this is our first look at some concept called single point grounding or ground reference. And of course, you can't make everything single point. It's not possible because, like, what about all the circuits inside the analog or inside the digital? They're not at a single. Maybe there's a single point there, but you know what I mean. It's something that has to be taken, taken kind of philosophically, at least to start with. Okay. So into the idea, what the heck is a ground loop? I've heard this term many times, and it drives me nuts because I think that sometimes people say, oh, there's a ground loop there, or, you're creating a ground loop. Well, what do they mean? What's going on? Here's a little picture at the top. Now, you can see there's a source on the left and there's a load on the right. And if they're connected together, that's cool. However, you can see that there are also 2 ground connections there. And the concept of this picture, and I would prefer to draw better pictures, but that's one thing, my graphics, I basically had to deal with what I could find on the internet. The picture means that perhaps there's some current flowing from the left to the right earth connection inside the quote ground, and that could cause current to flow in the bottom return lead. And so this is where really we're getting combining of currents we don't want. Okay. So if you want kind of an ad hoc definition of what a ground loop should be, if we're talking about it as a troublemaker, is a combination of currents from one path with the currents in another path, giving us some kind of problem. Okay. If it doesn't give you a problem, then darn it, there's no ground loop. That's my point. Okay. And we'll amplify on that a little later. Okay. Next picture is one that was actually W8JI made. And I say here, it looks like home, looks kind of snaky, but really it's kind of hard to make it any better than that. And even though it looks messy, it's actually not that bad because he's got a kind of a bus at the bottom where your common equipment is connected together. You've got to have all your coaxes and wires between your equipment, and then he's got everything plugged into a power bar. And if that power bar has got a decent ground, then that's not such a bad station. So what can we do better? What can we do worse when we're trying to do that kind of thing? Okay, new term. You may have heard the term bonding. You won't hear that in amateur circles much. It is of course in the electrical areas. I have my old copy of the 1994 electrical code, Canadian. This is the Canadian electrical code, which is underneath the basically the U.S. Electrical code and international as well, IEC. Bonding simply means connected together. It is an electrical tie between equipment. It is basically for safety, but it is a very, very important concept. And so it really is it's an engineering term and well-defined term. It's not like grounding. Grounding, of course, is defined in electrical circuits properly as well, but amateurs don't seem to have a clear idea what grounding means. Now, the AC mains, and I call it safety ground. The AC mains, of course, has two ground rods or a plate, and that is required when a service is put in. As a matter of fact, I was just reading this, and not a bad place to put it in here. This was section 10-700. A rod electrode should not be less than two rods, which shall be not less than 5/8 inch, unless it's copper, then you go to a half, less than 3 meters in length, and it must be pounded in 3 meters. I'm editing because there are exceptions and stuff to save a bit of time. And should be at least if you encounter rock, you got to bend it over and pound it in 600 millimeters below. Or you can use a plate electrode of about 0.2 square meters or greater in area, and that's going to be buried to 600 millimeters or your 24 inches. So that is done on every electrical service. You can't get out of that. That will exist at your house or place of business, wherever. That's got to be done as a matter of electrical approval. Now, there is only one ground permitted. And I'm stopping here. I want you to think about that. Only one ground is permitted. So what does that mean to you as an amateur? It means that if you establish another ground, you are breaking the Canadian Electrical Code technically. And the question is, if you establish more grounds, should your grounds be up to their standards? Maybe, maybe not. That's a question you're going to have to answer for yourself. I can't give you that answer. This is a kind of a floozy little diagram, but it gives us an idea here. And of course, this is only good if you have metal tubing or piping. And all of these wires, if you look at your grounding electrode at the bottom, and that is going to be tied to everything metal in the house, basically. That's of any, it's got to be, of course, tied to your main electrical service panel. And of course, if you have cold water pipes, of course, going to be tied to those. I would really suggest that you have a look at Jerry Spring's VE6KK's presentation on safety, which is in my references at the bottom, and that shows you how the AC mains and all that is constructed and set up. Incidentally, one of the grounding things that's allowed is they call these ground rods artificial grounds. So a grounding electrode can be a continuous conductive metal piping that goes underground. So you can, the electrician can use a water pipe system as long as it's long enough, and it can be a water well casing if you're on a farm. Otherwise, you have to put in the ground rods. So those are considered natural grounds, which is kind of interesting. Another thing that was in, I think it was one of the videos. I can't remember. It was the K0G one. He said, "Oh, you cannot, you shouldn't connect your gas piping to the bonding, or you shouldn't bond it to the electrical system." And it quite clearly shows in the code that that must be done. If you have an extensive piece of gas piping, natural gas piping inside the power house, it should be bonded as well. The video's argument was that, oh, well, you got plastic piping in the ground, so it could cause a spark or a fire. Well, yeah, it'll cause a spark. Why? Well, that's something we want to get into, and we want you to think about this very clearly. Okay, now we're getting into it. So what happens? What happens if we do get a surge here? And we can't avoid it. Here's a surge whacking the electrical service at the pole. And please take note that there's usually or should be a ground at the pole. In fact, sometimes between the poles that are 4160 volts, there is no ground wire or very little ground wire. So you actually have your service electricity flowing through ground, which is kind of interesting. So this surge whacks the service drop and goes through the gooseneck there into the meter and then along into your service equipment, which is a breaker panel. And hopefully that surge will exit and go to the grounding wire. Now, what do I say is by surge? This, my friends, is current. It's current. It's a lightning strike. We'll look at what that, or what it maybe even is just a partial strike. But this current it's a pulsing current, and it wants to return back. Basically, that's where it's going. We don't want it, of course, to go any farther into the feeder wires or into the house. Now, this does show kind of a panel board that's separate from the feeder. Well, mostly it's all in one place in our homes, as you know. Now, here is a very, very important piece of understanding. Some of you may have seen this, some of you may not. I remember seeing this years ago, and I kind of scratched my head. And until I got the concept of this and understood how it happened, once I did, then the light kind of turned on for me. So first of all, think about 20 kiloamperes, 20,000 amps in a 20 microsecond and multiple pulses. That's what's going to be whacking you, and that's pretty severe. Now, even if it's indirect, hits the ground or a tree like number 3 by a nearby object, still do some pretty bad damage because the currents are going to flow through the ground and maybe cause a lot of problems with earth currents, especially to underground equipment, like pipeline, buried cables, and that kind of stuff. So there's 4 different possibilities there. I don't need to elaborate. Now, before we go any farther, I found this little thing by VE7KK, and I just thought it was beautiful. And sure, it looks a little bit technical, but darn it, this is really what's happening. The problem with lightning strike is that you have impedances. Remember, I said the only way you get voltage, and we don't want arcing, we don't want sparks jumping between equipment, we don't want it starting fires. So in order to get that, it's because you're trying to push current through impedances that are too high. And sure, resistance here. So if you look in the second paragraph here, okay, so you can see DC resistances, only 1 to 10 milliohms per foot. So if you had, for example, 10,000 amps, smaller than what I suggested, you'd have 10 to 100 volt per foot of length. Now, that's not too bad. But what if you have a wire that has, kind of a very minimal inductance, Self-inductance is a bit of a weird idea, but this is, I think, fairly sound. If it had about 0.3 microhenries per foot, you take and multiply 0.3 microhenries and you take and put this into this equation. It's the inductance times the rate of change of current. And our rate of change of current, if it was 10,000 amps in 1 microsecond, okay, you end up with about 3,000 volts per foot of wire. So all you need then 10 feet of wire and you'll end up with 30,000 volts across a 10-foot piece of wire. How's that? It doesn't matter what the gauge of that wire is. It doesn't matter basically anything other than it's a straight piece of wire and you got 3,000 volts dropped across a piece of wire because of that lightning. And this is extremely conservative, okay? Extremely conservative. So short straight conductors are best. Even a right angle turn is not good if you can avoid it. You can't avoid it, but you also really should use a fairly large turning radius. And you should also mount that current turn very securely. One thing he doesn't have here is the force that's exerted. But if you took two 1-foot pieces of wire and put 20, 30,000 amps between them, you'd kind of find that you'd probably have a couple of 100 foot-pounds of magnetic force trying to push these wires apart. So if you have lightning conductors, they should be screwed down. Okay. So here's the story. And I annotated this so that you can go back. We're doing a lot of stuff tonight, and I really hope that you'll come back and look at the slides and think about this. So I found this neat little picture, and it's TVs, but and I annotated it from where it starts. So, ouch! Here we get whacked. So it whacks the cable TV entrance here into the house. And right away, you have currents flowing. The currents are going to flow from point 0 there over to point 1, and they're going to flow through the junk that's in the house. So from point 0 to point 1, let's say, just like we looked before, we've got 10,000 volts across this ground wire that goes between the CATV and the power entrance or the service entrance panel that's at the left-hand side, which is points B and C. In fact, we're going to consider them as a reference. We'll say that's, quote, 0 volts, everything. Now, it's a reference. These voltages are with reference to points B and C, okay? So you whack that, okay? What that will do then is it will cause, that CATV point to rise 10,000 volts above the electrical service panel. This is now going to be split. If you have a look at point 3 up there, what happened to my 3? Uh-oh, my 3 got left off somehow. So the TVs there, they raise about 2,000 volts above the cable entry. And then we have the remaining 8,000 volts between the cable entry and the electrical service or your safety ground. So because it hit the CATV, the conductors that go along there through your cable, so that's the cable supplying these guys. And of course, this could be your amateur antenna, and those TVs could be your radios. So now those radios all of a sudden go 8,000 volts above your power line ground there. And of course, 8,000 volts is enough to arc through just about any piece of equipment, any coaxes, or anything else. Now think about this. Even if you disconnect your equipment, if you leave coaxes lying around, if they're in proximity to another, what kind of stuff, even disconnecting stuff. I mean, you might as well go and pray because, I mean, that's a good thing to do too, but it's good to think about what you're doing because, you can have these arc overs. So do think about this thing. It's called ground potential rise or GPR. Okay. Now, how do we mitigate this problem? This is kind of out of my league here, the idea of lightning protection. Not much is done in Calgary. You go a little farther south in Nanton and you'll find that every doggone pole, service pole, telephone pole's got lightning terminals on it, the top air terminals. Generally, these down conductors go on the roof, and of course there should be a perimeter tie of some sort, or at least a partial tie, and that should be all tied to your electrical service ground. And you know, you can read a lot more about that as you wish, but now you can understand what they're trying to do. They're trying to get the ground potential rise to be uniform. In other words, if the whole house floats up, you know, 20, 30,000 volts above surrounding ground, that's fine, as long as all parts of the house rise together. It's kind of, that's not a problem. It's the difference between items that are inside the house or inside the shack. So let's leave lightning aside for a while and think about those currents. Let's get back to the idea of grounds and this common conductors. So what are intended currents that are going to be flowing in all the stuff we have? Number one, AC power lines. Of course, we've got, you know, our heavy main, and we've got the smaller green or safety wiring. We expect them to be low resistance. We expect them to pass harmonics of 60 and 120 hertz because we get loads of switch mode power supplies. A question of AC line though, do you want it to pass RF? And so that's something to really think about. Maybe in an advanced station, you're going to want to put your AC power line through a really good brute force line filter, so there's no RF or any noise that's going to come into your shack that way. You can do this even with a dead UPS. Most UPSs have extremely good filters in there. So a real cheap way to filter your AC line is to plug it in through a UPS. It's an idea I just saw here recently. Now, it also has a low resistance path, as we saw in the previous diagram, to reduce this possibility of ground potential rise. And of course, the more direct, the better. Unfortunately, you cannot control where that power line goes. It's kind of built into the premises. Second, intended currents. For lightning, conductors should be low resistance, but because the currents are very short in duration, probably, you say, well, 10,000 amps, won't that melt the wire? No, because, only for a few microseconds, the temperature probably won't even rise enough to get to the outside. It might, but in any case, it will stand it for a short period of time. And if you do blow a lightning conductor, well, it can be replaced. It is there for a purpose. A question we might ask right now, some amateurs have been using 1/4-inch copper tubing and soldering it. That is not in the electrical code for any kind of right electrical bonding. It's been suggested that if you had a lightning strike, you could melt the solder and then you got no correct connection. Hopefully you'd be inspecting it. So I'm not saying that soldering is out, but it's not something that I would necessarily recommend, okay? So you got to have low inductance, as I mentioned. Keep them short, keep them straight, keep them well mounted. And let's integrate them and bond them to any common RF stuff, to your radials and to your power common, okay? We're bonding everything together. That's really important. And before I forget, as I mentioned in the AC power line wiring, you are allowed to have only one ground. And that then would mean that, you really should be tying your ham shack ground rod, and we've all done that. I've got one outside my window here, and it's just a rod in the earth, and I use that as a counterpoise against my eavesdrop I was using as an antenna. But it's not bounded. It's not bonded back to the power panel. I'm not using it now. I'm going to be taking it back out, but that's kind of a no-no. Okay, so third kind of stuff, of course, is what we're all about, is our RF conductors, our coax. We want good shielding and we want good bonding. We want everything properly connected on our shields. And the reason is that any electromagnetic induction should really kind of pass freely back. So you're going to live under your antennas unless you've got a real good acreage, and so you're going to get radiated energy impinging on your coax and everything in a ham shack. And so we really, it's what do we call uh, it's a current in space, if you want to call it that. And so these return currents really need to flow back to ground. And I know they're kind of hypothetical, but they're well considered in engineering and modeling. And any currents that you have in your transmission lines, whether you're talking on 40 meters, whatever, it should stay in the transmission line and then go out to the antenna and then go out. It shouldn't come out inside the shack. And that's very important. Another intended current is our 12-volt station bus is some people decide instead of using 50 wall warts in one supply or two supplies, they want to make a big bus and put them all together with the power pole connectors. Just looking to see here if I have some. No, I had a little wee power pole thing, but I guess you've probably all seen that. Or other ways you can do that with just screw terminals and so forth. This is for you to decide. There's pros and cons. Separate wall warts are isolating. And so if you have a little device and you don't want its crap to get into other things, maybe the Walmart might be a better idea. On the other hand, you don't want wall warts typically that are switch mode. That's kind of a bad thing. And, so a station bus is good, but isolate it from other equipment and make sure that, it is well bypassed. Presumably that would be on your main supply. I guess you could add big capacitors to it, but you've got to make sure that the supply can charge it. So that's another topic. And a big one is telephone and LAN wiring. People who make big stations, contest stations, of course, have wrestled with a lot of this stuff. I looked at what Steve, V6 Whiskey Zulu, has done. It's not spectacular, his stuff, but he's put a lot of thought into how he's handled all this stuff. Um, it's important to use surge protectors. They're fairly cheap and stop anything coming in on your internet, your telephone, and whacking your radio. Particularly, you're doing digital. My flex here, right behind my shoulder here, of course, is connected into the internet directly. A thing that we must remember is we must keep these lines balanced. We do not want any kind of wiring coming in, something that you do after the telephone company. Hopefully they do it right, that their lines are perfectly balanced. But if you unbalance that, you'll get hum and you'll get crap in there. And if you have any balanced lines yourself, you better not upset that balance because then you're going to get interference into those lines. Okay. Um, and any other intrudes, not a very good word there, but anything that comes into any other equipment from outside, you must make sure it's protected. Okay, so that brings us to, remember, our theme tonight is currents. What are the currents that are going to flow? What do we want? What can we not avoid? And what are our unintended currents? Because this is really what, if you want to call it grounding, we've got to know what these currents are. Otherwise, we're just kind of we're just shooting in the breeze here. So unintended currents. Of course, power lines can bring in those spikes we talked about. You can have the line filter, as I mentioned. There's some excellent articles which I will show you. They're in the references list about toroids and so forth to take out noise on your station. That's a little farther down the road, but that's something you might need to do, especially if you're causing interference with somebody's TV or stereo or something. Lightning conductors. We really don't have very unintended currents here. There should not be much flowing in those conductors. They're only there to provide the return when we have that surge or, and of course, we may have snow static and there's always static around. So the lightning conductors can be conducting stuff. And so, and of course, if you have a few spikes, with static in the air or snow static, if you have a voltage drop in those conductors, and they'll induce current, etc., and you will hear that noise in your station. So again, a good idea to have good lightning conductors. Now, RF conductors and the shielding and bonding. This is a really big one, and I think it's something that the hams just take for granted. We do not want RF on the outside of shields and enclosures. That's kind of obvious, because we don't want it traveling, in a common conductor. You cannot avoid pickup on these coaxes and stuff. As I say, you live in an RF environment, but it's got to be dealt with, right? So anything that comes in onto your coax shields and so forth has to be dealt with, and we'll talk about that. Ground is not some magical black hole. It's not just a sink where currents are going to flow. We've got to think about how we're going to deal with this. And of course, the same thing is in reverse on receive, because it makes sense. If you can pick up your own transmitter, you can pick up the guy's noise next door. Somebody was just plaguing me here with a noise that was probably at about minus 70, minus 80, spikes every 140 kilohertz. Obviously a switch mode supply, probably LED lights or something, just wiped out all the lower bands. And thankfully it's kind of muted down lately. But if it's picked up on your antennas, there's not as much you can do about it. Now on your station bus, okay, we're going to look at those. They've got to have a good heavy conductors with good connections. Your station supply, that is probably 12-volt supply, should bypass all RF. That means it's got capacitors across it. And if you have a station bus, as I mentioned, like a 12-volt bar, you should probably keep it away from the grounding bus. Likely there's no interaction, but that's probably still good practice. And finally, these are unintended currents. Telephone and LAN wiring, of course, they're extremely ripe for transients and RF. That's a bad news for RF to come, and you get all this work done and the RF turns around and sneaks back in on your LAN wiring, your internet, or your telephone, comes back into your radio that way. And of course it's happened to a lot of us here. Many articles on chokes. And of course, you don't want to put a choke on the ADSL before you get your audio stripped off. You won't have, because that's up to what, a couple of megahertz or something. But do use surge protection. It's cheap insurance. Okay.
Peter, one question regarding the DC bus. Should your negative side of your station power supply not be grounded?
Yeah, I would expect that. That, of course, Jerry, is a point that almost all transceivers have the negative of their DC supply connected to the case. But presumably that's done inside the case and at one point. And of course, as you point out, then if you carry that to all the other equipment, then are we creating issues? If we, for example, we've got a transceiver, and now, okay, I've got an antenna tuner that's got, it's got, say, a couple of little lights in there. And now I'm connecting that guy in two places. I'm connecting it back to my DC grounding bus, and I'm connecting it back, through to my main, if you want to call it, coax ground, RF ground. So these are head scratchers. And remember, this is engineering. And Jerry, of course, is an expert in the broadcast application of all this stuff. And, I can flip the problem back to you and saying, okay, what's done in industry when you have a common DC bus like that?
Yeah. And I just kind of bring it up. We ran into a situation once where the DC supply was not at ground potential, building ground potential, or AC potential. It was a Ubiquiti microwave system, and it was PoE going up to the tower top system, and Ubiquiti actually uses a differential voltage to do a system reset on the microwave. So without grounding the DC power supply to system ground, every time you plugged in a laptop into the LAN connector to do something, it would send the system back to a factory default on that.
Yeah, you'll
And
get a
so
different.
we had to go through and make sure everything in the repeater site, actually, that the AC ground, the system ground, and the DC power supplies and battery were all at the same potential.
Yeah, yeah.
So,
yeah, and you do have to investigate this stuff, and that's the reason why I want to I want to look at the principles here, because the principles mean that you can look at things analytically, and you can decide and troubleshoot. I would recommend, I think, in building up a station, that you don't go all whole hog for a DC station bus to start with, and I would add those pieces, carefully and selectively. For example, if I had that little conductor going into my antenna tuner just to supply some 12 volts, I think I'd be wanting to wrap some ferrite, around some ferrite cores or something, to make sure that crap doesn't go through there on the RF side of things. So yes, there is not a simple answer to some of these things. Now, another thing that is well familiar to telecom guys is the concept of what they call crosstalk. Crosstalk is crosstalk and common mode are the same idea. If you have multiple pairs in a cable, as you do in, say, Cat6 or something like that, as you know that they are balanced conductors, and the signal on them, as Jerry's mentioning, is what we call differential. It is not grounded, and the signal is between the two pairs. So if you have any kind of unbalance, then you can get noise appearing into that cable pair, and that is a problem, right? I'll show you a picture here shortly. Um, the other thing we can get happening, which is really the same thing, is that we can have leakage through our coax shielding. You may not be aware that ordinary coax like RG8 and those kinds of things, RG58, 8X, typically are, what are they? I don't know, 80%, 90% shielding. I can remember back there was a copper shortage back in the, I think it was back in the 80s, and Radio Shack was with CB boom was going crazy, and we were doing. It was a summer job. Was doing some installations, and I'm telling you, you could read a phone book through the braid of the RG8 that they were producing in those days. So it kind of made you shake your head. Yeah, you'd get some signal up to the antenna, but it did not provide shielding. Okay. Um, and of course, the common mode, our typical problem, as you probably know, and why we use balance, is that this displacement or space currents that I talked about can induce RF on the outside of coax, and this may get into other stuff, and so this is the crosstalk or cross coupling. Now, I'm going to go to the next slide and have a look. This is a little picture on common mode interference. I didn't quite know how to organize this best, but it all kind of fits together. So if you look in the upper left, here's a balanced system. That green generator is supposed to be sending, and it could be unbalanced, wouldn't matter, but that green generator is sending in the green loop, it's sending currents through those two wires, the top wire and returning the bottom wire, etc. Now, if you apply this common mode noise, the red one at the bottom left, then you will get current flowing in the bottom wire of the circuit that you're interested in. Will that hurt you or will it not? But that's what common mode is. It's a signal with respect to some ground or outside reference point, not the differential that you're trying to achieve. Now, if you look to the upper right over here, where we have this chunk of coax, and I like this picture because it's horizontal, how we think of things, but it's the same thing as an antenna. No, here's a dipole here, but what's supposed to happen, and I hope that you remember this from basics, that the current that flows is supposed to flow. Let's look at half a cycle. Let's suppose current flows this way on the outside. Remember skin effect. It's flowing out the outside of the inner conductor, and it goes into the capacity and inductance of the dipole antenna. Now, meanwhile, back at the ranch, back at the antenna, the charges happen to be flowing this way in your antenna. And what we really wanted to do is to flow on the inside of the coax, all the inside, the whole inside of the coax. That's where the currents are supposed to be. This is where your 40-meter signal is supposed to be. It's supposed to be inside the coax. But unfortunately, some of these return currents, and I showed it the other way, they could be, the diagram, I don't know why, I didn't realize this. He should have had his arrows going this way, but that's okay. Some of the currents can flow on the outside of the coax. And this is called common mode. And this is where we might want to do some choking and so forth. That is a whole separate topic, how you do that, and about ferrites and chokes and balance and all that kind of stuff. And it's another presentation I've been working on for a long time, and it's hard to, I think I have a good one that I borrowed from another guy. So if you guys really want to have a look at it, it's an engineer from the States, and he's given me permission to use this presentation. So if we want to do that here in the club, I'd be pleased to do one on balance and common mode chokes. Now, to the big picture at the bottom here, the point of this thing is these common mode currents can flow or are flowing on the outside of the coax. So what does that mean? Well, what it means is that this can get into other pieces of equipment. Now, how could it do that? Well, as you know, two wires that are parallel can induce currents in one another. So if I got a current flowing here, I can get current flow in another wire. So this is your house wiring. Then the currents here could induce current flow onto the house wiring and then get into your stereo, or it could get into, like mine, I had a paper shredder key up when I keyed up on 40 meters. That was kind of interesting. I'd called it PSI, which some people would think is kind of supernatural, but anyway, paper shredder interference, who'd think? Uh, anyway, these currents can and will cause havoc. Now, how do we deal with them? Usually with a common mode choke. But you know what? Sometimes they won't hurt anything. So just think about they're there. How does a common mode choke work? Well, here's a picture over here of probably the best concept of it. This is for a balanced line. But you can see here that the way these are wound, if current flows one this way and that way, and I won't go through the pluses and minuses, but the idea that if there's a current flowing from A to C, returning from D to B, the net magnetic flux in the core is zero, and so nothing is induced. However, if you get currents flowing both ways in the same conductance, the two will cancel each other out, and that will then prevent the what they call a common mode noise. There's one of these in every telephone and every modem. That is a very, very common thing. They're in every switch mode power supply and so forth to keep crap off your AC line. So, there's a little piece of learning. Just look for that guy. All right. So our common grounding, as we mentioned, we've got to watch it because they can carry currents that can induce noise into other ones. So what to do about it? We've mentioned this. Maintain our balance. Keep good shields on your coax. That means put your connectors on, guys. Put them on properly. And avoid close parallel runs if they're not bonded. Space your AC runs physically if you can, your AC power bus from your RF tie ground, and space your antenna from your shack if you can do that. Here's the top picture is a picture of crosstalk. This is called near end crosstalk between cable pairs. And the bottom is just another one, as we mentioned before, how we may interfere. So, and a lot of these slides, as Jerry and I talked, you can have a look at them later. Okay. So really, this is our conclusion for part one. there's nothing mysterious or magical at ground. It's not a black hole. Any common conductors should provide a low impedance path, but they should block currents that you don't want. So a lightning conductor should pass these high current pulses, but your RF choke should stop stuff going on the outside of the coax. Number three, you cannot avoid common paths or grounds. And, people that say there's an RF ground and there's a lightning ground and there's an AC service ground. Yeah, but in some ways it drives me crazy because, they're all a system. And I urge you to think that way, okay, to integrate them. So what are we going to do? We're going to have a look in part two. Really want to look at what's available, and we'll roar through some slides that show you really typical grounding scenarios for stations. And of course, I suspect there'll be some questions about that. And remember, we're optimizing safety and performance. We're going to engineer this. We're not going to just use folklore and uncertified stuff. So if you do any reading, make sure you read the good stuff from ARL and some of the experts. Not the quote self experts. So I got some homework for you right now. One thing I have not mentioned is electrostatic damage. I come into the room here, it's wintertime. I usually touch something metallic before sitting down at the rig or the computer because it's been known to whack things like my thermostat. So where does this fit in, guys? And as they say on BBC, back to you, Jerry.
Okay, very good. So Peter, am I right in assuming that the second part of this will be more of a practical applied troubleshooting kind of approach to the problems that you've outlined in the first part?
Exactly. We want to see pictures of stations and of some standards and that, and how you'd connect your stuff together, the best ways to go about it, and some pictures of of ground bars and things like that that you can buy or make.
One of the misconceptions about a ground rod, especially whether it's AC ground or people calling it a safety ground point, is 99% of the times you put a ground rod in the ground, and if you put 110 onto that ground rod, it will not blow the breaker. If it's got a ground fault breaker on it, it'll trip right away. But a standard breaker that most people have in their houses and that, it will sit there and pull probably 7 or 8 amps and just heat the ground all day and that.
That's so because of our ground here?
No, that's standard in most places. Now you can get ground with very high conductivity where you might get up to 12 or 15 amps, but very, very seldom when you, like I say, put 110 onto a ground rod, it will blow the breaker and that. So when you look at just the physics of what's going on at that point, now you have a length of ground wire that's energized with a potential across it, and that ground rod is now radiating that with a potential difference in the ground around it and everything. Up to, I think Peter hinted on some of this and some of it, of so much per foot or per meter actually around that round rod can become energized. And this is where you get into step potential around energized ground and that. So if you've got a ground rod really close to your house and it's had 110 volts energizing it, and you've got a water pipe or something or anything else that's within like a meter of that, you can have up to 70 volts just from inductive or conductive from the ground being energized in adjacent equipment. If your coax is laying on the ground, a connector or something, then it becomes energized in that. So like I say, it's a real misconception that a ground rod will trip the breaker and save you in that.
Wouldn't that represent a very lethal situation if you stepped around that ground rod and you had that sort of potential?
Yep, and that's a lot of the training for any electrical people that work around power lines, down power lines. It's called step potential, and it's the distance between your 2 feet and how much of a potential that you can get current from 1 foot through you body
Right.
parts through the other one and that. So you're taught, if you're working around it, to keep your feet together and kind of either hop and don't fall down, or to just shuffle your feet to get away from the energized area and that. But like I say, around a ground rod that has 110 or 220 onto it, that ground will be energized in that.
Now, if I have a ground rod or I actually have 3 ground rods at the base of my tower, one for each leg, and it's all connected, that ground potential is potentially different than my house ground on the panel, because that's a cold water pipe, whatever, in a different location, maybe 30, 40 feet away from that.
Yeah, and if you go back to Peter's graphic about GPR, and if you took your outside antenna, removed that ground on that graphic, and then started looking at the potential of your equipment in the building between where the lightning strike was and the building ground, 8,000 volts of that was dissipated into the electrical ground. Now you've got the full 10,000 volt potential through every piece of equipment in the house, because that ground rod outside was not tied to your electrical ground. And that. It's what I tell people when it comes to lightning. I hate talking about lightning because there's no rules when it comes to lightning.
Don't get hit. That's the rule.
Well, yeah, just get out of the building. And that, but,
yeah. So let me just ask this. I've wondered this for a long time. So I have coax coming in from my antennas, which are theoretically the ground of the antenna is grounded to the mast, which is grounded to the bearing, which is grounded to the side of the tower, which is ground through the ground rods at the bottom of the tower, which theoretically at RF radio frequencies are different grounds, different potentials, I should say. But anyway, assuming that that's all grounded and the shield of my coax should be at the same ground potential as that comes in to my station, should that not be grounding that to the radio, which is then grounded through the center plug of my power cord, which is then connected to the house ground?
What if you're running your radio on DC and the negative side of that power supply is not grounded?
Well, I don't do that, but that's a potential. Okay.
But, yeah. In the broadcast or the professional side of it, your coax are grounded at the top of the tower, they're grounded at the bottom of the tower, and they're grounded when they enter the building and that. And all those grounds are at the same potential and that.
Okay.
So anyway, I'll throw it back to Peter here. I just
ahead,
wanted
Peter.
to throw that in about ground rods will not usually trip an AC breaker and that.
You guys are driving me crazy because you're using the word ground too many times. I mean, what is ground? Ground
Right.
is ground is it got dirt in it. This is what
Coffee
this is.
grounds.
Yeah.
Okay,
I mean,
the station bonding point then. Your
exactly.
common bonding
Exactly.
point.
This is why I prefer the word bonding,
That-
because that means you're connecting them together, right?
that-
Ground means, if you really want it, it really means a return of some sort, or hopefully, zeroing a potential. So it's something that, we might strive to achieve, but doesn't seem to be, right?
In the second part of your presentation, do you go into Kirchhoff's current law at all? Or we'll save that for another night.
This is inherent in exactly that slide number 1, Jerry. That's exactly where I wanted to go. And I see that Andre has a question. I'll get back to Jerry TL's question. Really, everything should be bonded together. And I think maybe once we finish the presentation, I think maybe that'll answer the question. I heard ground so many times so that my mind kind of boggled. So
yeah, it's habit, I guess, more than anything.
Andre says, is there any point in measuring ground potential between them? If they're bonded together, how could you measure a ground potential? That's my question. if they are not bonded together and you measure a potential between them or you measure resistance between them, you're looking at earth grounding resistance, I guess. So, you know.
Yeah, so the question is that I have 3 grounding rods around the house, plus the one from obviously from the electrical connection here, and they are all connected together. It's just, again, it's mostly for lightning protection reasons.
Yeah.
Also, we have lots of solar panels, so there's a grounding going all around them. And the question is that, is it any harm that, they are all connected together at the moment, or there should
They
be?
absolutely must be. I mentioned that in the first part, and that according to electrical code and everything we're doing, you've got to tie all that stuff together and as directly as possible. So absolutely, you've done the right thing there.
Peter, just a thought there is that so very strong language on there must only ever be one ground, and maybe there's some misinterpretation there of only one ground rod, right?
No, yeah, you're absolutely right, Dana, and that's the wording in the book. There must be only one ground, and they didn't say ground rod; they meant one connection. And so you're right, and that I'm glad that you emphasized that point that everything must be tied together. And as I said, I have this one outside my window, and it's not tied back, and it should be. It's not a good idea. Drinking game. Question, is it better to ground the disconnected cables or just leave them lying around? Yeah, so what's ground? Where are you going to connect them? Where's that current going to go? Very, very good question.
I've seen ungrounded cables at a transmitter site, and the tower was hit by lightning, and it blew. The cable literally danced around, and there were 3-foot arcs coming off of that to the equipment in the rack, and that. So don't leave. They will bounce, and that. But tying them to ground, at least that energy is going to go. Away from the building and away from your equipment and that. So yeah, just leaving it disconnected is not a good thing.
I agree. And when my little station, we'll talk, I think it's a time for us to get going, but we're going to talk single point grounding, grounding panels. And that's what you want to do. You want to be connecting these unused cables back to your single point ground. And that's really, that's what has to be done. I used to do that simply by connecting it to the water pipe, which is almost right adjacent to ground. I had a very ideal station where my outside electrical ground, my tower ground, all that stuff, I'm using ground too many times again, was it was all within a couple of meters of one another. So we'll get back at it here. One of the things, have a read of this, people. This guy here, and I'm not saying that he's an idiot or anything, but we're not discussing first electrical protection ground as mandatory, blah, blah. He says, from the start of the point, you have RF circulating through your station instead of inside your coaxial cable as a must do. And so forth, this idea of RF circulating and that. And my question is, why is it circulating? What does that mean? What's the cause of this? And so this is mumbo jumbo. And this is stuff that you will read, so be very careful. And this is followed up by KY6LA, Howard, which is, he's an engineer, and he's referencing Ward Silver and QST and this diagram, which I'm going to be using. And he says, no, he says it's sound engineering principles, that the theory of the circulating currents and that is not, is not really what we're focusing on here. So there are many articles. This EHAM from the ground up, I thought it was a simple article. Jerry says it's, there's quite a bit. I'll use these diagrams. It's in the reference. Phil Salas, 85X, tons of excellent articles. There's an article here on second floor grounding by Tom Rausch, W8JI. We won't have much time to get into that. It is in the links. and we'll show you all of these products here. EHAM has got product reviews on, how the heck do I get that bar at the top to go away? That is really frustrating. Vince, help me out here. For some reason, yeah, the only thing I can see to do is to minimize that a little bit, and then I can see where I'm going here. This is an article on Lightning Luxurion, very interesting article. And some of the stuff that's available from KF7P and lightning suppressors from Alta Delta, stuff for surge protection that's available. And as we have time, we'll have a look at all these bits and pieces. There's an Amazon, only 14 bucks or something. No, this is a, yeah, it's not a very good one, but and another article by WHAI on common mode currents. So those are things we want to have a look at. So okay, let us start into part 2 here, and this is going to start as a little bit of a story. We're kind of thinking of Ken and Joe and this Steve W6GOT W6OAT, I guess it is. But I did talk to Steve on my KX2 one time. No, KX1. I talked to him directly and even had my picture taken and put it on his YouTube thing. It's kind of funny. So what we're going to think about here are what are the common grounding conductors? What return paths are there for RF? And these 5 paths I've written down here, mostly for us to think about as we go into every station situation. The AC power line, the lightning conductors, the RF conductors, the DC station bus, and any other wiring like telephone and LAN. And of course, what's his concern there? Well, mostly exposure and falling over backwards, not having sunscreen, and staying away from lightning. So that station probably has almost no transmission line and of no concern, right? Okay, so what happens if we bring that transceiver into the house? And it's kind of a busy, cluttered slide, but I suppose you've got a vertical in the attic, like I know a couple of you have already done. And your AC is coming in from a power bar in the station. And probably you haven't got really much else in here. If we look at our 5 paths, your power line maybe is a little more exposed. It could pick up some RF. Lightning in the attic, probably no worse than any other stuff. So you can kind of, I guess, sleep fairly well and not thinking I haven't added to the problem. I certainly haven't cured a problem, right? My RF conductors, shielding and bonding. Let's make sure we've got decent coax. And as I started to mention decent coax, there is coax that has an integrated foil on it. For example, the LMR series 200, 400, 600 have a foil shield, as does most cable TV coax, and this provides much better
Peter?
shielding. Yep.
We're not seeing your slides.
What?
We've got the one on common mode currents.
Really?
We were still seeing your web browser, Peter. The
Oh,
web page.
really? Okay. Is it up now?
Yeah.
Okay, sorry about, thank you. Thank you for telling me. Okay, so you did see the web browser though, eh?
Yeah.
Okay, yeah, okay, so here's the previous one was if I can go up a slide here. I don't know, how do we even, there we go. Yeah, this is the picture up on the mountain with a minimal station, okay? And then if we bring that station inside, as I say, there's a little antenna, looks like a homemade one there in the attic. Looks like he's got some coax coming out of that, drilled through the siding on the house. It's nice if you can sneak up below the siding. If sometimes that even go through the concrete. And there's a inside a little bus bar in the station for grounding stuff, connecting it all together, and then a nice ground rod and a proper type of clamp. So as I say here, you may have some exposure of your power line to RF. We'll have coax, which we've probably made a good connections on. We got no station bus, we got no telephone and stuff, and we're not worried too much about it. At VHF, low power especially, we're not likely to have any TVI or RFI. And, if you wanted to go a little further, you could connect your antenna to, to a lightning conductor, drill a hole somewhere and take it down the side of the house. So that's a pretty minimal concern. Now, suppose we add HF antennas. Maybe we got a vertical on the ground, and maybe we've got an HF end-fed with a matching transformer outside. And of course, we start adding this stuff, and we'll probably want an antenna switch, maybe an antenna tuner. And, I would like to draw a picture here as we build it up, but this is a simple little picture that, that I found. Here's your transceiver and an SWR bridge, because you want to watch those HF antennas. If you haven't done HF, you'll soon realize that we got to keep an eye on those antennas. It's not like VHF, UHF. Usually you just put those things up and forget them. And the only time you find out they're not working is when you don't get any answers, right? But HF, we want to monitor that SWR under tune conditions every session we operate. Certainly not all the time, but you haven't been on the radio for a couple of months, so you surely want to check that. So let's have some kind of a direct connection to Earth wherever we can. We've got our antenna wire coming in the side of the wall. We do want a decent common bus for all our AC power line stuff. It's a good idea to have this right here. What I've got, and I don't even want to show you because I've got one of these octopus plugs here at this temporary station. Andre's smiling because he's seen it. And don't do what I do. Don't do what I do. Do what I say, right? And of course, lightning conductors tied to ground. Keep your RF away from your audio and stuff. It's always a good practice to keep high-level cables away from low-level cables. TV and radio stations, I know Jerry's smiling there because, they even go to they even bundle stuff or even have separate raceways in some cases for stuff, okay? And when we go digital, let's provide some grounding and surge protection for that stuff, okay? Okay, now here's what we want to do. And this is a very important idea. Number one, let's look at the dotted lines that are going down here. Somehow or other, you want to make yourself a common tie point for the, well, let's call them grounds, but they are the chassis connections. That little typical wing nut. So here's, this is for all us wing nuts. We're going to connect those cables all together somehow or other. And this is going to be a backup. And in addition to the connection to that third wire, that green safety ground that's on your electrical service. Now, this is an ideal situation here. This is the dream of the ham station. Let's have a ground system outside. So these are multiple rods probably. We'll talk later. Your coax is coming in from somewhere and it's going to attach to a ground plate. We're going to be called a single point grounding plate, SGP, can't even say it, single point grounding plate. And that coax entry is really our common place as much as possible. And this, of course, is the place that you want to have your lightning surge protectors like a polyphaser or alpha delta. Some pictures. The one at the top is the one from ARRL that we were talking about. And I didn't show you all the web pictures, but there is another one on lightning protection that was published in QST, well worth reading. Do look at the references. I spent about 2 weeks establishing all these references and finding the web links because I've got a whole library on this stuff and I didn't have the links. At the left is kind of a dream. Look at that heliax and look at all these are gas tube surge suppressors. I mean, yeah, there's a lot of bucks there, but you know, we got to start somewhere, and you might start with just one suppressor and one chunk of coax. So at the bottom is another drawing, same idea. There's your you know, copper strip or braid. I'll show you some pictures, but uh, who's the Texan guy? W6GYF. Trying to remember his name now. Just watched the video. He took some of that perforated pipe strap that was copper plated, real copper if you can get it. He fastened it to the wall around the back of his station. Yeah, W6CYF, Tinker John, he calls himself on the web. And this is tied outside to your grounding system. Another good way to do it, if you don't want to go to Georgia Copper and buy yourself a $200 or $300 US bus bar, take a chunk of copper pipe. 1/2-inch pipe is great, and you can use clamps on that pipe. You can drill into it and put screws into it, whatever you like. There are two schools of thought on this, and we'll talk more about that, whether you go kind of in parallel or whether you try to make a rat's nest maze and try to go everything into one particular point. Here's a homemade station bar. And I think it's a pretty good idea, better in a room that only has one outlet. This would be very good if you could, in your station, have, like for example, 240 volts, and your 240 could supply this, and these could be split outlets on different sides of the line. You know, I was in a thrift store a while back, and in there was a, you know, I grabbed it as soon as I saw it. It wasn't on sale yet. They just put it out, so I paid the maximum price. But it was like a 6-foot long power bar, and it was made by Hammond. As soon as I saw that Hammond name on it, I knew it was commercial stuff, and so I grabbed a hold of it. So if you get a hold of one of those, even the Princess Auto ones, if they're good enough Chinese make, inspect them. But you could screw that to your desk and behind your equipment, coil up all your line cords, and then plug all that together, and now you've got yourself you know, a kind of a decent AC bus.
Peter, question. In the last few slides, you showed the antenna coming in and the rig and the antenna tuner and so on, but it never showed the AC bus or the AC outlets for any of those equipments.
Yeah, this is, as I say, they're considering them separately. The figure 24-8 here, these are the wing nut or external, if you want to call them ground. They're the external common connectors. And this is another form of bonding that's applied. So you do have your electrical supply here, and you do have your DC supply, but this is strictly that, you know, is that common connect to all the chassis or cases of your equipment where possible.
Right, but the AC line has to also be connected. The green or the ground of your AC outlet should be also directly connected by the shortest cable possible to that copper bar.
No, absolutely not. The AC safety ground is handled by the AC wiring. So, you know, and again, I suggest you have a look at Jerry Teal's slides here. That plug that you're plugging in here has got that third wire, so-called grounding or U-ground, you can see at the bottom. And that is the only tie back to your AC line. So you do not go into that box and you do not tie that back to your back to your bus bar. It would not be a good idea. Those two systems should be kept separately. If you feel that there's RF coming down that power line, or you know you've got problems because of it, then I would suggest what they call a brute force line filter. You could try many turns of your line cord on a toroid, although that's not likely to help because of the heavy currents. But no, Jerry, a very good question. You do not want to tie those together in the Hampshire.
So the ground that's coming from your antenna outdoors is at a different potential than the AC panel ground.
It could be. It could be. But again, we want to, I guess we want to have a look at what currents might be flowing. And that is the key here. These currents in this picture, the currents that might flow through here are currents that were radiated by your antenna and are going to land on your equipment. So we want a return to ground outside, if you wish. The other possibility is there's leakage currents from the coax that may appear on some of this equipment. Again, we want a coupling to as near as possible to outside. I want to put a kind of a vision in your head right now, and I mentioned this to Jerry TL many years ago in the years of TVI. People were advocating a plate on the ground, on the floor of your ham shack, right on the concrete floor, on the back of the wall. Presumably it's a basement. And, you know, this is something I would do if I was starting building right away. And I might still do this in my basement shack. The problem is corrosion. If you use galvanized, it'll end up or steel and end up rusting. But if you have a big sheet of aluminum or brass or copper or something, and I mean like 2 by 4 feet, put this on the ground on the floor of your room, and then put the floor on top of that. This provides coupling, and that lossy earth, it will take RF off of stuff better than almost anything you could consider, particularly if the shack is in the basement. So no, this is, if you want to think it this way, this is an RF return, Jerry.
So you don't connect up the ground from your panel to the ground from your RF sources.
Not here. We'll look at where we do that connection. That connection has to be done outside.
Do they end up de facto connected through the chassis anyway?
They do, yes. Yep.
So there could be a potential difference. You could see a spark if you're plugging in your coax to your chassis, whatever rig you have.
There could be. They were getting into a bit of an issue. Some radios have capacitors to ground from line either side. These are supposed to be special, what are they all, KX or KY capacitors. Where you get into problems is like this Drake 2B behind me that does not have a 3-wire cord. And those things can have, a little bit of AC on the chassis, and that's where you probably will see the spark. Connecting your coax up, if you see a spark, it's probably because you've got some static coming down that antenna, and the outside of the shield of that coax is not properly bonded to the grounding electrodes outside. So you shouldn't be seeing any sparks. You shouldn't be seeing much difference in potential. The reason is there are no currents flowing. If there are no currents flowing, how can you have a difference in potential? There should be no currents flowing in your green safety wire. If there is, we're in real trouble. That's why we do not have the neutral and the green connected together at the outlet, okay? Because there is current flowing in the neutral, and there you can have difference of potential, but there should be no differences of potential on the green wires, and that should be at the same potential as your outside, hopefully. And we'll look at some pictures later, okay? Now, if we start to build up the station where we want, more power, not only are we going to need the dollars, obviously, although A11H is about one of the cheaper linears, but now you're going to have more AC current. You're going to have then possibly more noise coming in that way. Certainly, you're going to have higher power in all antenna components, and we went through that with Andre, saying, okay, you better test gradually to see if you blow up your coax or your balance or your antenna or whatever with 500 watts. And if you do have a linear, I suggest you start with 300 or 500 watts before you start going to the full 1,000 or so-called 1,500. Your 5 paths, of course, bear thinking about, but mostly you're going to have more RF to get in where you might not want it. Now, the linear itself is supposed to keep the RF inside the cabinet. This was the big deal in the old days. I got a real nice Johnson Viking from Jerry And those guys had just acres of shielding in them, whereas the cheaper, heat kits and that did not. And the RF would sneak out and it would go on the outside of the cabinets. Like, for example, through the meter holes. Johnson actually shielded the back of the meters. So that is not a hole in the really expensive stuff. RF can't come out. Think of RF flowing kind of like as if it were, I don't know, like something out of Gremlins or something. And it would, the back of the panel would seek out and seep over everything and sneak around the outside. So those RF currents are really what we want to avoid. And we want to make sure that, if you want, they've got somewhere to go. They want to get radiated. So let's take them outside. Okay. Just some pictures. There's a nice LP100A. Jerry and I have one of those. And in fact, this is the linear setup I have. 500 kPa 500 and 500 watt tuner. There's a Daiwa watt meter. You certainly want a watt meter. But you're going to need more cables for linear. You're going to have a push to talk, of course, microphone, or sorry, your connection, push to talk control, and probably PC control. This might even have a separate power supply. And certainly it's going to have to need higher current from your AC mains. So you've got to plan for that. You've got to think about it. And you must have power monitoring, SWR monitoring. The LP100 has a special line that will shut down the linear amplifier if the SWR is too high. So that's a beautiful feature of that particular unit. Just some reference here, it's kind of a ludicrous diagram, but different kinds of outlets. Probably the outlet that you will want for your linear is the 6-20R for a 240, 250 volt wiring. At the bottom are some bigger ones. There's some stuff for the 120 volts. The ones that I got the circular tabs are called twist locks. As far as I know, the most recent electrical code, which I think is 2019 or 2020, now states that all new wiring must have tamper-free outlets. And I don't think it said anything about the about 220, 240 volt ones. So I think they do accept the range and the dryer ones because they're plugged in all the time. But you can always claim that your linear outlet was there when you bought the house, I guess. I'm not suggesting that, but finding a tamper-free outlet might be a challenge. It does accept the twist locks. So you might have to go with your linear. For example, if you want 15 amps, the L615 or the L620, and those are readily available. So that might be the way you want to wire your shack. Some other pictures. The top, that's a 6-20. Yeah, it is. Yeah, 240 volts. There's tamper resistant. Some more pictures. And at the bottom left, some other pictures of outlets. You can look at these later. These are readily available. Wikipedia is really great for this stuff too. Now, here's the good stuff. Here's when we want to go for a tower, and we're going to have some kind of a beautiful either an entrance panel, this which is actually on the side of the house, or a junction box that's at the tower. So we're heading for this single point grounding panel. That's really want to do, and hopefully this is going to integrate problems with our lightning conductors and our RF conductors. Of course, this doesn't say anything about the other concerns there. The little bottom left-hand picture is something that I wanted to add to this presentation and just haven't gotten to, and that is worrying about corrosion as you start working outside. I wanted to put in my reference slides. I might still do that. The galvanic series. It's not recommended that you connect copper directly to aluminum. You should have a stainless steel barrier. Some people actually even isolate it from the zinc tower leg, and just a piece of stainless steel in between and using stainless bolts is a way to go. If you do that, always use anti-corrosion compound, for example, Noalox or Penetrox on all these connections. Any stainless steel bolts, if you've ever used them, must have a lubricant or else they'll gall and you won't be able to disconnect them. Okay, now we're getting into it. This is what we want to do here. Here is a nice example from that EHAM article. You can see the lightning protection on the down conductors. You can see the ground plate at the shack entrance. You can see that all ground rods are tied together. And as Dana said, one ground connection. That's really what we mean. It is a unified ground or unified bond, all bonded together, but they make one single common ground connection. They must be connected back somewhere to the AC service ground, and there's a real headache here, and some, I won't call it controversy, but there's a choice that we have to make, and in some choices are easy and some are not. Copper to galvanized or zinc. I would have said aluminum, but galvanized is not too bad. And actually, I put copper right on my tower. Some people say you shouldn't even mix tin copper and bare copper, but in Alberta, I have seen very, very little corrosion problems that way. Certainly in a coastal environment, you better watch out for it. Or if you bury it, if you bury your connections, that's a little different. Something called thermite welding. Ever done any of that, Mr. QLT? That is a very beautiful. It's basically like the kids' volcano project for school. It's a bunch of chemicals mixed and poured into a little mold, and then your conductors are welded together. I will make a comment right now, something that you may not realize. Proper ground connections are typically clamps or crimps, and there are proper crimps. In the electrical code, you're not allowed to join conductors unless they are connected with proper crimps. Now, the crimping and clamps are actually a form of welding, because what happens, and I'm sure if you ever used a wire nut, you will know that a good wire nut connection that's been done, if it's been left there for a while and you disconnect it, you will see that the wires don't just fall apart. They were actually welded together. And if they were clean, they're actually bonded at a molecular layer. So don't turn up your nose at crimped connections. Here's the scenario. So we've got a tower. You'll see it's better to space the tower from the house. We have a document that suggests this. You'll have your coax coming down, and this Motorola document, which I'll show you later, recommends that it being no more than a meter above ground. You will normally do it at ground, which is excellent. You may have soldered connections. I kind of would, kind of question that. I would really say crimped or clamped connections. So I kind of disagree with that a bit. I would say that this is the poorer choice. He's used copper tubing. I guess that's good. And I don't know about the slope of the ground, but it's really good to get that coax shield connected to the tower base if possible. I tend not to do this if the tower is very close to the ground plate. I think you're probably, it's a bit of a compromise, but I don't think it's severe. 8 feet apart is a good idea for ground rods, and we'll show you why that is a good plan. Oh, incidentally, if you have radials, they're all connected here too. Radials for your vertical. And here's a suggested plan. It's just kind of a matrix of 8-foot rods and wires connected between them. And, they're all connected. In fact, if you wanted to make more connections between all the other rods, there's no harm in doing that. And so I will say to the guys out there, will say, well, isn't that a ground loop? Well, I don't know. What's a ground loop? You want to go around in circles, you go for it. But why would you have any kinds of circulating currents? Quite clearly, if you have lightning whack the ground anywhere near any of these ground rods or pipes, you want the lowest possible inductance and resistance connection to the next one to dissipate that charge. You want to spread that charge out as much as you can over the whole area. And that's the key to that. And so if you have a radial system, all the better, you know, connect all that stuff together. And you can see the ground plate coming into the hamster. Now this one looks very busy. I will let you look at this at your leisure. I left it to last. It says the same thing as everything else, but it looks quite complicated, but it's really not. You know, here's that grounding and the grounding kit here. There's a rod. This is connected to your AC power panel, as we said. Okay. There's, of course, your AC power services coming in here. These are the safety grounds that, uh-oh, sorry about that. These are the safety grounds that go to your equipment and to your power bar, as Jerry Spring was questioning. Okay. We are not connecting that back over to that bus. There's the safety ground must be handled on its own over here. Same thing with the cable box and the phone box. They all go back to that power panel. And at the ham shack, hopefully you've got the single point grounding panel. And you say, well, I don't want to go out and spend $1,000 on one of these panels. Or I keep doing that. I haven't got that light touch. But that hopefully, you know, that you would have some, and this isn't very clear here. It says phone service and cable TV service, but what it means is that your protectors would be here, so that your surge suppressors and whatever would be tied at that single point grounding panel, so that you do not get a difference of potential between that and any of your equipment. Okay, that's the whole idea. And now you can see that you've got perimeter grounds. You know, if you're really great, you can get that go all around your house. You know, if this was a pipeline, like a compressor station or something, or a broadcast facility, you'd probably have a metal building, and you'd probably have a band around the middle of the building, all around at equipment height. And then you'd probably have a perimeter ground, even in the concrete. Okay.
So Peter, what I was asking about basically is your single point ground, where everything's kind of coming in. You were suggesting that that ground connects up with your AC power panel ground outside. Is it okay to do it inside?
No, I would not do that. I would not do that. Your connection to your electrical service is this line right here.
Because
That's
the
the
power
only
panel ground, as far as I can tell, only goes to the gas line, which is in my basement near the panel.
Now, as I mentioned, your AC power panel must have two, and it must be either connected to a good metallic water line, to a well casing, or it must be connected to two ground rods 8 feet apart, or there is a plate that is buried. I just had mine redone at the cabin, and he ignored my two ground rods. He put in a brand new plate, buried it down 2.5, 3 feet, and that's the ground. Now that ground, you are right, Jerry. How do you get at that? How do you actually access this ground? Is that perhaps the question?
Yeah, there must be outside somewhere.
No, not necessarily. That ground could be buried under the concrete in your basement.
Which is
So that might not be immediately available. So that's a very good question. So probably what you will be wanting to do is provide a hole through the house somehow, follow that out. And usually there's a whole bunch of services there. Your cable TV comes in there as direct as possible. Some number 6 bare or number 6 screen. You could probably use number 8, but you want to ground that or connect that, bond it to your AC power panel right there. And usually you will see that wire. So I didn't get any pictures of split bolts, but that's what you would use. You would use a split bolt, and you would simply parallel those two wires. You do not want to cut the wire from the, from your AC power panel. So basically what you've got in here is you would get a hold of that wire in here and then make your own wire to come out and then go to whatever connection you need to there. So no, do not make any other connections inside your AC service.
okay.
Yeah. Um, So we're basically at the end of this stuff. I will show you more pictures and some equipment, and then you can sort of say, let's tease all this out. In my reference slides here, I have some really amazing supplier hardware that I found for copper bars and straps, grounder busing, grounding, and lightning arresters. And there's some manufacturers' websites, articles, and presentations that I've viewed. I've checked the links, and I've checked to see that everything I've shown you here is available in the links. Finally, I want to mention this standard, which was gratefully refamiliarized to myself by Vince. This is the Motorola R56 guidelines. It is 2005, but if you can trouble yourself, I would pick that up and have a look at it. This is the commercial guidelines, and it makes you kind of, yep, this is the way things really need to be done. And of course, all throughout Alberta and everywhere else, all these outside and inside installations have to follow these kind of guidelines for whether the communication sites, cell towers, like I say, compressor stations, whatever they are. Have a look at chapters 3 or 4. And finally, at the end of this, I just wanted to remind you that, it is kind of discouraging to look at all that needs to be done. But don't be overwhelmed. You've got that ground rod outside. Maybe you haven't got one yet. Maybe you're just going to use a piece of copper pipe. And there are many, many videos, how to drill a hole using the water system, or how to power it in using a Hilti hammer, or things like that. All these are individual problems, but do get something. Copper pipe is soft, but it's cheap. So if you can get that into the ground, 1/2 inch or 3/4 inch copper water line, that makes excellent and cheap ground. Do use that. Start small. Use your electronics problems and keep up the dialogue. As I say, what I want you to think about is there's a lot of ways to solve the problems, and get some advice and keep that dialogue up. And as I say, there's if you think, okay, somebody says, oh, you got a ground loop there, well, question, like, what is it? Like, what is causing the problem? Here's some stuff. I won't belabor this stuff from Georgia Copper. Wire is round, it's good. A braid is nice and flexible. A copper strap is the ultimate, and it ain't cheap. I question braid in some ways. I don't think it's as good. We've got that weaving path, but copper strap is nice. Look at that gorgeous stuff here. And there's a beautiful bus. Some people will have nice wide straps, one paralleling each other all onto this bus from each piece of equipment for those wing nut grounds. Other people will try to tie to one big point and then just have a whole bunch of copper braids in a star pattern. Some people claim that's better. I can't say one's better than the other. And maybe I could ask Jerry TL to remind me if I don't make a comment again on it, about grounds and ground conductors, and that if you have RF on them, we're talking in relationship to the wavelength of the energy, okay? That's a very important idea. So when people argue about, should I have a whole bunch of braids, one from each piece of equipment, all tied like a rat's nest back to one bolt, or should I have nice straps or to each individual people to a ground bus? I think it doesn't make a heck of a lot of difference. You might try an alternate if you get into troubles, but I can't see how there's any difference for most situations. For me, I'll use a fairly small bus for this, and I'll use some fairly cheap braid, probably that I get off a coax. If you can get better stuff, that's great. Or what the heck, if you've got some nice number 8 wire or number 10 wire that's flexible, I don't see any problem with using that for your station bus. Some beautiful stuff. Waterproof boxes from KF7P Metalworks. Look at that, eh? The one on the bottom left is an entrance panel. The bottom on the right is actually a junction box meant to be used at the tower. Here's some more pictures of the stuff, just amazing. And, you know, look at that. Isn't that just absolutely gorgeous, eh? Just amazing stuff. And it doesn't have to be copper. You know, there's nothing wrong with aluminum, particularly if it's not, there's not a lot of water in there. These surge suppressors, though, are they're meant for inside service, so you wanna be careful with that. Other gorgeous stuff. The one on the left for tying to a tower leg, like how can you beat it? You know, you'd want to waterproof the coax boots, but you know, tie that on your tower leg, and there's a nice ground clamp for your wire to come up. Upper right, same thing. That one mounts right on a ground rod. That's good for smaller installations. The bottom right-hand side, another tower commoning block or grounding block, if you want to call it, and and I kind of like, you know, the idea of going into the wall and going through. To me, if you can do that, I think that's nicest. But you know, your mileage may vary. Here are the links, and here is the last point that I want to kind of expound upon. And this is the Motorola standards from you know, and I just took these two excerpts. Reducing the height at which the transmission lines leave the tower, enter the building, can reduce the susceptibility to damage from lightning. Remember, we're trying to integrate all this stuff. We're trying to say, well, there's no difference between RF and lightning grounds. We want to keep them together. We want to integrate them. And same thing with the AC power grounds. We want to integrate it. So keep it less than 2 feet above the facility floor. That's pretty easy for us to do. Another one, here's a picture of it. 1, 2, 3, 4, best, and so forth. And so pretty easiest for us to do number one. Increasing distance between tower and building. Well, in the city, you know, we're lucky if we can get a tower up at all. But if you have a choice, if you can get it a little farther away, the theory here for, especially for commercial facilities, it's most likely that lightning is going to hit what? The little metal shack or the tower? Of course, it's going to hit the tower. And so, you know, the idea of the currents could be dissipated by the time they get to the tower. And here's their picture. You can see the ring grounds all around there with various rods and everything bonded together, you know, not only the raceways, the fences, all that kind of stuff. Next time you're on the C train, I know at COVID times you're probably not riding, but I always enjoy looking at, you know, you're stopped there. Look at all the bonding wires, the green wires, all the fences on that C train are all connected together because they're near that high voltage stuff there. They don't want induced currents. They don't want anything in the ground flowing and causing two pieces of fences to be at different potential and maybe causing a shock or causing corrosion. So have a look at the C train, you know, so frost fencing, you know.
So Peter, question, is it always a good idea to put radials from your ground rods, like at the base of your tower, which would distribute the currents more evenly around your backyard?
Absolutely. And I was thinking, Jerry's had such good luck with verticals, and I want to try one or two, but I got myself a vertical that's technically does not use radials. But now, after doing this, all the research on this presentation, it's definitely, and I didn't include it, there's another piece of the references here that show how those radials can really help lightning protection. So it's a good question, and definitely. I'm going to be pouring a slab for garage out in BC. I think I'm going to leave some of the wires sticking out of there so I can connect to them. Anywhere you can run conductors that are in the ground is very good. And another one, Jerry and I both said, Peter, you got way too many slides here. Another slide I wanted here was something called an UFER ground, UFER. And I was just watching a video last night on that. And this guy, particularly in the desert, etc., where there is not really good conductive ground, it's found that concrete holds moisture and provides a better ground in many ways. So if you want to look up UFER, unfortunately, I forgot to put that in the reference, UFER. And basically what it means is that your tower bolts, the tower bolts, or if your tower is buried in concrete, that in itself is providing a very good ground. You must add to that. And if you can bury a conductor in concrete as you're pouring, if you're going to build a new shack somewhere or build a garage, the requirement from the code, though, is that you must have the conductor coming out before you make a clamp connection to it. So you would make your servet or your your split bolt connection to that wire outside of the concrete. And it's for a proper AC service ground, there are requirements of how deep that's buried and where it is. But certainly any kind of wire in concrete is a very good ground. Last thing, last couple here. There's a ground ring. That's beautiful. If you can do that, shows you more grounding, steel belting, kind of idea like that, just to reiterate it. And lastly, something that I didn't think about, and I love to think about this thing now, is this grounding sphere of influence. So here it says here is that the idea of a rod that, 2 times the rod length, that the sphere of influence for a ground rod is commonly thought to be a radius around a rod equal to its length. And it achieves 94% of its resistance value at this radius. 100% is at approximately 2.5 times the rod length. And this is IEEE. It's been tested. So there you go. That's really how good your rod is. So if you got an 8-foot rod, then you've got about 8-foot radius around your rods. And that's why they say to space them about 8 feet apart. Because if you space them more closely, they're not really very effective in connecting to whatever is down there in the in the earth. So, here's another paper, Bixie. I think this is from Philippines or something. But one last time to think about it. In the upper right are 2 pieces of equipment, A and B, and only resistance in their ground lines. And so A is causing a drop of 1 amp over 10 volts, okay, which is over 10 ohms. So that's 10-volt drop. The other one has got 1 amp through 5 ohms. That's a 5-volt drop. So of course, A to B at the earth point is a 5-volt difference. So there's a 5-volt difference between there. And that's why there's currents flowing in grounds. So if you're wondering about ground loops, or if you're wondering why you ground or any point of this at all, it's because you can have this happening. You can have currents flowing in the earth or through a conductor that you don't want. Now, have a look at the bottom picture where they tied equipment A and B together. Now, yes, you've still got some impedance in your ground line. Maybe it's, inductive. That doesn't matter. The point is now it's 2 amps times 10 ohms. That's 20 volts, yes. But the 20 volts is common to the 2 pieces of equipment. And you will see that in commercial equipment, they keep that in a common rack, that each rack is kind of kept separately. So you have all your stuff connected together in one rack, and then all the racks would be connected to a common point. I kind of hope this helps you guys. This is just some of the pages that I had up. Oh, yes. And the last thing I will mention, 2 monumental papers. One by Chuck Councilman, W1HIS. I show this in my advanced class. And one by Jim Brown. And this is how to use ferrites to reduce the noise that comes into your station by reducing the pickup on all your lines, your transmission lines, your power line coming in, your internet, telephone, and everything else. And similar papers on building the contest scores there. So this is the very ultimate end of it all. You do a good job of all this, and not only will you get rid of that RFI to the paper shredder and stereo, but hopefully your receiver will quiet way down, and the only crap you're going to get is going to be coming in your antenna. So took a little longer than we'd hoped, Jerry, but
Well, that's the rule of multiplying by pi. So,
Yeah.
or pi over 2 or something. But anyway, yeah, it was very good, Peter. A lot to think about, and a lot of work to do, actually, when you think about as you build your station and you have all these pieces of equipment and they all need to be tied together. And but you've got to think safety first, and then you've got to also just about everybody I know who's put together an HF station has had to deal with grounding issues. So there's a lot of research and a lot of head scratching and all that kind of stuff. So and it's good to know there's a lot of experience around that because most of us have gone through a lot of that have had HF stations. And it also applies to VHF and UHF, whatever. It's all scalable. So, and I'll turn it over to Jerry QLT to add some final comments on that.
Yeah, I just wanted to say one trick that I used to use when testing an install. And you were thinking maybe you're getting some antenna or common node current, of RF back through a system, is, you power it up and you've got meters dancing when they shouldn't be. And Peter is saying, some potential difference on equipment, and that is run your station into a good dummy load. And if it eliminates a lot of those issues, then you know that it's RF coming back probably on the coax shield, and that's causing that. If it cleans up your problems and that, then your install, your grounding and all that is good. And the only difference is now you're radiating from the antenna. So it's got to be a, coax current, common mode current that's causing the problems and that. So just like I say, it's a shortcut of kind of breaking it down into blocks. But if it works fine into a dummy load without any problems in that, then you may not need much other, grounding or bonding, issues of that.
So, for example, if you put up a 20-meter dipole and you're coming through your stereo at home and you're turning your dishwasher on, which I know someone who's actually got this very problem, you would start by doing the dummy load test, and you would see that everything looks fine with the dummy load. So you've got RF coming back on the coax, which is probably due to a little bit of a mismatch of impedances, and you're getting RF reflected back.
It could be RF, just radiated RF off of the antenna into the equipment also, and that.
So your antenna could be the problem because it's too close to your house.
Yes, saying. Or too much power.
Or your cable, your coax is actually coming close to your AC power lines.
Yeah, but now you've at least eliminated or broken it down. Is it an internal problem or is it an external problem?
Yeah, let's back up a minute here. Dishwashers are not intended to receive RF. I forget what the other issue is, but the problem is with the dishwasher. The problem is with the other appliance. Less, according to the ISED, that you have a field strength greater than a certain number. And so, yes, you want to solve the problem, but well, like I say, you're probably going to have to attack that one at the dishwasher.
Okay. That's not too easy, I don't think, taking the dishwasher out to put chokes around the wires, but you may have to do that.
Just turn the dishwasher on before you go to bed.
Or pull the breaker.
Well, yeah, but yes, but I think, and Jerry's point about testing is very good. Can you determine, for example, if there is RF on the power line? And that might be something that you could do a test of. Vince and I had a real go around of some issues in his ham shack, and there are issues that really, really get your head scratching. I don't know if we have time to hear from him if we solved anything there, but it would be interesting to hear more about this particular problem, Jerry, about the dishwasher, etc. And I would say that the very first thing this individual wants to do is, has he adhered to our basic bonding and grounding principles? Is there that single point connection for all of this stuff? And is that tied to an outside ground rod, which is tied back to the power panel? I think that if you have not done those things when you have a basic station, then you're kind of just flapping in your breeze.
Okay, very good.